Hi all, today once again I want to welcome you to today's class. Today we'll be looking at the mole concept and the mass percent. Let us get on it. I hope you have watched all the videos, and at this point I want to say again that if you're missing anything, if there is anything that is not clear to you, do make up time and see me in the office so that I can help you figure those things out. Let us start the class. So the first thing we're going to be talking about today is the molar mass or the formula mass. Remember earlier we in the last section of this class we talked about how to calculate the molecular weight or the formula weight of molecules or ionic compounds, and we're going to take that a little bit further. What is a molar mass or a formula mass? A formula mass or a molar mass simply represents that molecular weight or the formula weight that we calculated, but this time you attach the value of grams per mole to it. So if you calculate the molecular weight of a substance or the formula weight of a substance and express it in grams per mole, or you can say the mass of 1 mole of that substance, that is what we call the molar mass or the formula mass. And since we did a lot of example on how to calculate the molar weight, what you simply need to do is to go you can go back to those examples, and by the time you express them in gram per mole, all of them will become the molar masses. But I have a good example here. So here we have glucose molecule. Here glucose has 6 atoms. Look at that. Glucose has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. And so what does that mean? That means that we're going to try to do this as we did before in calculating the molecular weight. So now 6 atoms, 1 atom of carbon weighs 12.01. And I'm going to add that plus 1 atom of hydrogen weighs 1.01. But how many atoms do we have here? We have 12 of them. We multiply that by 1.01 plus there are 6 atoms of oxygen, and each atom of oxygen weighs 0.00. If you do your math correctly, you're going to get 180.18 grams per mole of this substance. What this simply means is that 1 mole of glucose molecule is equivalent to, or can we say weighs exactly 180.18 grams per mole. Again, if you look at this is a simple conversion unit, is what we've just arrived, but we're going to talk about the import of this as we move on. Again, it says another element, urea, has this particular formula. We can determine the molar mass again. Remember, the molar mass will always be measured in grams per mole. Okay, let's get at it. Again, there are 2 atoms of nitrogen. Remember, the parenthesis has to multiply whatever that we have inside. So this is going to be 2 bracket 14.01 plus, now again there are 2 atoms inside of hydrogen inside. We're going to multiply with this 2, and that's going to give us 4. So 4 atoms of hydrogen total times the weight of 1 atom of hydrogen is 1.01 plus we have only 1 atom of carbon, 12.01 plus an atom of oxygen which weighs 16.00. And when we add all these things together, you find out that we're going to get 60.07 grams per mole of urea. So these 2 things we've just calculated represent the molar. So simply, molar mass simply represents the molecular weight or the formula weight of a substance. Express it in grams per moles. So we go to the next thing. Let's talk about the so-called mole concept. Remember, this chapter will basically address this. The mole simply represents a bulk unit of counting atoms, molecules, ions, or any other specified entities. I usually tell my students in class that the buying and selling of atoms and specified entities are actually done with the mole. That is what the mole represents. The mole is a highly microscopic unit which really measures most of the things that we cannot see. So we can actually trade with the moles if you are in the merchandise of atoms and molecules and particles and formula units. So now, a mole as a bulk unit can simply be used like a dozen. Remember, a dozen simply means 12. 1 dozen of anything, of course, 1 dozen of anything, a dozen of anything represents 12 of that thing. So if we say a dozen of X, it's going to represent 12X. So that is what a dozen is, a dozen of X. Okay, maybe let me use another color for my X, so that will make it a little bit more, will make it cleaner a little bit. I like making my notes a little bit cleaner. So 1 dozen of X will give us 12X at any point in time. So what that means is that a dozen of roses will give us 12 roses. Of course, egg is the commonest thing that is sold in dozen. This one we know it all the time. Go to grocery to buy your egg. 1 dozen of egg will weigh 12X. What does that represent? Now, so we can simply use the fact that a dozen, of course I'm going to write it again, a dozen represents 12 of that stuff to make up a conversion factor. Now let's use it as an example just to remind ourselves of what we did in chapter 2 of in chapter 1 when we did conversion unit. Now you see it says how many dozens, we're looking for dozens in this case, how many dozens of egg are there in 24X. Of course, knowing that a dozen of egg contains 12 eggs, this is a very wonderful conversion factor. What that tells us is that we can set up a conversion factor for these two. How do we set up the conversion factor? Remember again that now I can have two conversion factors here, that a dozen over 12x, or I can say 12x over 1 dozen. Now, remember, our responsibility is to convert from x to dozen. That's actually what we've been asked to do. So in doing that, I'm going to use any of these conversion factor. Now, but since I'm starting with x and I want to end in dozen, what it means is that my dozen has to be on top. And which one am I going to use in doing this calculation? I'm going to be using this conversion factor at this point. I'm going to be using this one particularly because the dozen is on top. And if I use that one, what do? I'll multiply this very number given by this. So what that thing means is I'm starting from my 24x, then I'm multiplying it. I'm going to use this. I'm going to use my, you don't have to use this, but I want to use this to do this. I want to use this my line because it makes my destiny a little bit easier. Now, 24x. Remember, this is easy. For you to cancel x, the x has to be down, which is exactly looking like what we have here. So this is going to be my 12x is going to be down here, and then my 1 dozen is going to be up here. And what that simply means is that if I cancel it, x, we cancel x, and then if you divide 24 divided by 2, that is going to give you 2 dozens. So if you have 24x, you just have the equivalent of how many? You just have 2 dozens of egg. That is exactly what you have. I'm going to write my dozen a little bit clearly so that that's going to be much more cleaner. So I'm going to make this cleaner. I want to make it cleaner a little bit so that makes it easy. So this is going to be dozen. Okay. Again, let's use this one. It says, how many eggs do we have in 36 dozen? So I'm not going to be writing out. I already wrote out the two things we're going to use. I used this on the first one because I wanted my dozen to be on top. Since I'm looking for how many eggs in 36 dozens, I'm going to use this one here now. So I'm going to use a different color to just mark out that one because that is what I'm going to be using to solve the second problem. So what that simply means is that I'm going to be starting with 36. I'm starting with 36 dozens of egg. And then, now, since I'm using this, remember, half dozen. So it makes sense that my 1 dozen is going to cancel and my 12 eggs is going to be on top. So dozen, we cancel dozen. And what that simply means is that You multiply 36 times 12, and that is going to give you 432x. And this will be your answer. So basically, this is what we're going to do by the time we start talking about the mole concept. The mole itself just constitutes a way of counting atoms. Now, for atoms, we're not going to use those. What are we going to use? We're going to use a number called the Avogadro's number. That's what we're going to use. So we're going to see the relationship between Avogadro's number and the mole concept. So the Avogadro's number is the number of atoms or molecules or specified entities, like ions or formula units, in a sample of an element of that compound. That is exactly what it is. So it means the number of particles. Molar actually measures the number of particles contained in a sample of an element or compound with the mass exactly, or we can say in grams, with a mass in grams equal to the atomic or the molecular weight or formula weight of that compound. So what it means is that the mass of any substance will weigh a particular mass in grams equivalent to the mole of that substance. So what does that mean? Let's see an example. So if you have 1 mole of X, 1 mole of X, of course, will contain this. Remember again, I said this is what we call the Avogadro's number. The Avogadro's number is the bulk unit of counting atoms. So this Avogadro's number is equal to 6.022 times 10 to the power 23x. And then this will also be equal to the molar mass of X. Now, if you look at this now, we've set up like two conversion factors from this. What it simply means is that, let's use a good atom. 1 mole of potassium atoms will contain this number of potassium atoms. And potassium occurs as an atom of a pure substance, a single atom K. And the mass of 1 mole of potassium atoms is 39. So this is a good conversion factor to solve any problem regarding K. So following factors can be generated from this. What does it mean? Let's now try to make this into pieces. Now we can bring a relationship between a mole and this guy. That means 1 mole of potassium here is equivalent to this number of particles of potassium. It could be atoms, it could be ions, it could be any other specified entities too. Now what that simply means too, we can also say that 6.022 times 10 to the power 23 potassium atoms is equal to the mass of 1 mole of potassium, which is 39.10 grams. And we can also say that the 1 mole of potassium atom is also weighs this particular mass in grams. So from this very fact, we have 3 conversion factors that we can use in solving different problems. Now, so the basic thing we're going to be taking away from this place now is that the mole itself is used as a conversion unit. Remember, the mole is measured actually, you see, the mole just is the relationship between the mass and the molar mass of a substance. So what it means is that it can, since it has 2 units attached, it can always be used as a conversion factor. So the molar mass and or Avogadro's number are used in mole to do mole conversion problems as shown below. What does it mean? Remember, look at this. What we have in the previous chapter by setting up these 3 levels of conversion can be related from this table. We can convert from mole to mass. We can convert from mass to mole. Look at the 2 double arrow using the molar mass as a conversion factor in this case. We can convert from mole to particles and particles to mole using the Avogadro's number as a conversion factor. Again, we can convert from mass to particles using the molar mass as a conversion factor, or we can convert from particles to mass using the Avogadro's number as a particle. So it's important for you to understand this, my beautiful flow diagram in doing conversions. So you can convert from any of these, from one of these to another. And what matters is that you're going to be able to make up the conversion factor and find out the relationship between the 2 things you are looking for at that point in time. So let's start by solving problems. Particularly, we'll have a couple of number of problems I'm going to solve here as well again. Remember, if we solve problems and you practice a lot, you're going to always learn these things to proper understanding. So silver weighs about 107.8 grams in the periodic table. If you look at, I'm looking at my periodic table here now. You have to get yours out. Silver is element number 47. It weighs 107.87 to 2 decimal places. Now, it says, how many moles of silver are in 20.770 grams of silver? What do we do? So we just move on. So we say 1 mole. The first thing you need to do, we are looking for the relationship. We want to convert from grams to mole. That's basically what this is telling us. Okay, let me write this cleaner. So from the idea of this question means we are going from grams to mole. That is the question asked. You're going from grams to mole. So what we need the relationship between these two. So, but remember the way we defined both mole or atomic mass. We know that silver is a single atom and it weighs 107.8. What that simply means is that a mole of silver weighs equal to 107.87 grams of silver from the periodic table. That's where you're going to get this from. You're going to get this from the periodic table. From the periodic table. Let me just write it in case someone is going to listen to the class. So that is from the periodic table. That's where we get this from. And then what that means, we can form two conversion factors here. I'm going to do the first, try to form the two of them. Then other times, I'm going to be a little bit faster and you're going to try to form the tables yourself. Okay? So I'm going to do it. So this is a table. This my table doesn't look clear enough. So I'm going to try to make it look clean. This is table. Now, so again, what that simply means is that I have two things I'm going to be working with. So I'm going to work with two types of conversion factors. So I can have a mole of silver divided by 107.87 grams of silver, or I can have 107.87 grams of silver, this is silver, divided by 1 mole of silver. So these are the two conversion factors. Now, however, I'm going from grams to mole. What it means is that my mole has to be on top. So what that simply means for me is that using this will be the correct thing at this point in time, and that is what I'm going to use. So I start. Again, you can draw a table. You don't have to. I'm going to draw a table here. So I'm going to start from the given. What are we given? So I'm going to start 20.70 grams of silver. I'm going to try to draw a table. Now, I'm going to use this, and that makes sense because if you look at it, this is going to be down, and it will easily cancel with this one. So this is going to be 107.87 grams of silver, and then 1 mole of silver. And what does that mean? What it means is that I'm going to cancel next. Grams of silver cancels grams of silver. And when you put this into your calculator, what are you going to get? You're going to get 0.192 moles of silver. That is the answer you get. We go to the next one. It says, how many atoms of copper are present in 1.5 mole of copper? Now, we're looking at, it says, how many atoms of copper? So what that simply means, we're going from, look at what the question simply says, mole to atoms. That is what we're looking at. And the relationship between mole to atoms, so remember, an atom is a specified entity, and the relationship here will be the Avogadro's number. So let's put it down. So let me go back to my red. So what it means is that a mole of copper will contain how many atoms? Remember, the Avogadro's number has no unit. The unit depends on the entity specified. So here I have this. That a mole of copper will contain 6.022 times 10 to the power 23 copper atoms. What does that simply mean? What that simply means for me is that I can use this as a conversion factor. Since I'm looking for atoms and I have my mole, I'm going to try to start again. I have my 1.5 mole of copper. And you can draw a line. You don't have to. I'm going to draw a line. So what that simply means is that I'm looking for atoms. My atoms is going to be on top and my mole is going to be down. So my 1 mole of copper is going to be down. My 6.022 times 10 raised to the power 23 copper atoms is going to be on top. And there again, I'm going to cancel with my green. 1 mole of copper cancels moles of copper. And the answer we're going to get here, when you punch it correctly, will give you 9.0 times 10 to the 23 copper atoms. And this becomes your answer at this point. So then let's go to the next problem. You see, my style of class is always solving a lot of problems, and that is the only way you get better in some of this. It says, how many moles of neon are present in 2.85 times 10 to the power 24 atoms of? Again, I'm not going to write the conversion factor, but I assume at this point, you always know that a mole of neon will contain, of course, 6.022 times 10 to the power of 23 neon atoms, if you remember. So, what I'm going to do here is that we're going from atoms to mole. That's exactly what we're doing. So, I start from what I was given. Remember, I was given this. Then, if I'm given that, I'm going to put it in. So, it's going to be 2.85 times 10 to the times 10 to 24 atoms of neon atoms. Then I'm going to multiply that with my conversion. Now, of course, I want to get it in moles. My moles is going to be on top. So I'm going to have 1 mole of neon, and then I'm going to have this down. 6.022 times 10 raised to the power 23 neon atoms. And then again, I cancel. You look at it, neon atom cancels neon atom, and what I have is left in moles of neon, and that's going to give me 4.73 mole of neon, and this becomes my answer. So we go to the next problem. It says, what is the mass in grams of 2.22 times 10 to the power 22 moles of bromine? Again, a pure bromine atom exists as diatomic molecule, Br2. So we're going to calculate the molar mass of that guy, remember. So it's going to be, since we are looking for the mass, we're going to calculate the molar mass. So there are 2 atoms of bromine, and 1 atom of bromine will weigh 79.90. And when you multiply that, this is going to give us 159.80 grams per mole of bromine. That's what we have. Now, again, just remember, if you write your conversion factors well, you can always try to write everything completely. It doesn't pay. Of course, you know that 1 mole of bromine will always give you how many atoms? It will give you 6.022 times 10 to the power 23 molecules, because this is molecules is involved now. This exists as a molecule, molecules of bromine, and this also gives you how many. 1 mole of bromine atom we weigh how much mass? We weigh 159.80 grams of bromine. Now, if you look at these 2 problems, our problem is pointing us to the direction that we're going from molecules to mass. If we're going to go from molecules to mass, we're not going to use the mole. The mole is not relevant to us. So what are we going to use? We're going to be using these 2. Will be our conversion factor. Again, we start from what we were given. We were given 2.22 times 10 to the 22 bromine molecules. And then now again, I'm going to multiply this. Since I want to take away the molecules, what am I going to use? I'm going to put this down. So this will be 6.022 times 10 to the 23 molecules. And then on top, I'm going to have what? My molar mass, 159.80 grams of bromine. Now, if you multiply these 2 stuff, this will give you molecules of course, let me go back. I didn't put my bromine. This will be Br2. So if you cancel again, this will cancel this. And when you multiply this by this and divide by this, you're going to get what mass? Make sure you punch this correctly into your calculator. The answer you will get will be 5.89 grams of Br2. The next question. Now, we've been talking about atoms and molecules. What about compounds? We can also apply the knowledge of mole concept to compounds themselves. So we know that 1 mole of any compound is a sample of that compound with the mass equal to the grams in grams to the molecular or formula weight of that compound. We remember that we said it earlier. What it means is that a mole of this guy, a mole of this sulfur trioxide will contain this number of molecules, because this is a molecular compound, and we weigh this particular mass. And this mass simply means adding the weight of sulfur and oxygens in this molecule and knowing the molecular weight and expressing it in grams. So we can use this and generate a few factors for this molecule. What it simply means is that a mole of sulfur trioxide will contain this, of course. A mole of this is going to weigh this particular mass. Or we can say that the mass of this will contain this number of molecules. And we can apply any of these in calculating and solving problems depending on what we're asked to find. So now let's do this quick problem. Having known that conversion factor already, says how many moles of oxygen atoms are contained in 15.39 grams of that. Okay, let's try to write it down. Remember, if in this molecule of SO3, what it simply means is that 1 mole of SO3 will contain how many moles of oxygen? Look at it, 3 moles of oxygen. So we can easily say this. Oxygen atoms. This is legit. That's what it means. But if you look at the question, we're looking for from grams to moles of oxygen. So there's no way we're going to be using this, because we're not going from mole of, if we're going from mole of sulfur trioxide to moles of oxygen, that makes sense. But we should remember that the mole of this guy weighs how much? Again, we should remember that the mole of this guy will weigh 80.06 grams of this guy. The mole of this will weigh this, therefore, and this will be equivalent to 3 moles of oxygen atoms. This is very logical to make this assumption. So the basic thing we're going to do here is that we're going to be converting from grams of sulfur trioxide to mole of sulfur trioxide to moles of oxygen atoms. And that makes sense because we have that here. This is the conversion factor we need to do that. This is the conversion factor we need to do that. So we can even write 2 conversion factors from here. This is easy. We can make up 2 conversion factors. Okay, let me write it towards this side as usual. So from here, I can say 80.06 grams of sulfur trioxide will divide 3 moles of oxygen. Or I can say 3 moles of oxygen will divide 80.06 grams of sulfur trioxide. That is what we have. We can use any of those 2 conversion factors to do the work. So let's move on. Which one are we going to use? Since we're looking for the moles of oxygen, what it simply means is that the mole of oxygen will be what we need, and that is going to be at the top. So basically, I'm going to be using these to solve the problem. Moving on from there. What am I have? So we're going to convert, I'm going to start with what I was given. I was given 15.39 grams of SO3. I'm going to be multiplying that, of course, again. You can always use the table. That seems easy to be student. I want to be using that more consistently now. Then look at the conversion factor. 3 moles of oxygen and 80.06 grams of sulfur trioxide. Let's see if this cancels. If I get my green, look at this. Grams of sulfur trioxide cancels grams of sulfur trioxide. And we only left with 3 moles of oxygen at the top. And that makes sense. And when we put this in our calculator, that is going to be 0.573. 7 moles of oxygen atoms. So this will be our answer at this point in time. So and this is what we're going to get. So we'll move on to the next problem. The next problem, it says calculate the number of molecules of sulfur trioxide that will contain 98.07 grams of sulfur. Again, let's remember this is as it relates to the molecules. We're trying to see how we're applying this mole concept inside the molecule, inside the compounds themselves. So in this compound now, we want to calculate the number of molecules of this guy that will contain this particular mass of sulfur. Now, what do? As usual, again, we try to find the relationship between this guy and sulfur. We can easily say that. So the basic problem we want to solve here is that we're going to be going from grams of sulfur to, this is grams of sulfur to molecules of SO3. That's basically what we want to do. This is what we want to find. And then we'll try to draw a relationship between these two. So here now, of course, again, we know that a mole of this guy, a mole of sulfur trioxide, contains how much of sulfur? It contains 1 mole of sulfur, of course. That's what it contains. And, of course, a mole of sulfur for us weighs how much? If you look at your periodic table, the mass of sulfur is 32.06 grams of sulfur. So, but this has not helped us here yet, right? Because we're looking for grams of sulfur, which will have the grams of sulfur to molecules of sulfur trioxide. But we just know that a mole of this guy will also contain how many? We know that a mole of sulfur trioxide will contain 6.022 times 10 to the power 23 molecules of sulfur trioxide. So we can even write it here, it doesn't matter. Always try to make this relationship long, and those equivalencies doesn't matter. So I'm going to put it here, 6.022 times 10 to the negative 23 molecules. So what that only tells us is that now we got what we want. From grams of sulfur to molecules of sulfur trioxide, this is exactly what we have here. That conversion unit is what's going to serve us. So we start again from what we were given. We're going to start with this mass. So from here again, 98.07 grams of sulfur. We have this U unit. And since we're looking for molecules of sulfur trioxide, we're going to put these molecules on top. So what that simply means is that this guy is going to go on top, 23 molecules of SO3, and then this mass is going to go down. Now, the best thing that works when we do, when we do the dimensional analysis of factor unit method in solving problems is that make sure that the unit cancels out well. The moment your unit cancels out, you know you're 100% correct. You don't need to worry whether you're right or wrong. So if you put this in your calculator, I'm doing that now, you're going to get 1.84 times 10 to the power of 24 molecules of your SO3. And always give your answer and give the unit, because you can't just have a number that does not have a unit. If we go to the next problem, it says use the factoring label method from the factors obtained from the preceding relationships given for sulfur trioxide to calculate the following. Again, I've been using sulfur trioxide as a good example here. So we're going to use those conversion factors we had earlier to try to solve these problems. So let's do it. What that simply means is that now it says the mass in gram of 1.5 mole of sulfur. Again, in this case, we're going to be using 1 mole of sulfur trioxide contains the molar mass. The molar mass is 80.06 grams of SO3. This is our conversion unit. And we want to convert this mole into mass. So what do? We start with what we're given. So we're given 1.50 mole of SO3. And then we have to cancel the mole because the mole is going to be down. So 1 mole of SO3 will give me 80.06 grams of SO3. And if you do your cancellation well, mole of SO3 will cancel out, and our answer is going to be 120.09 grams of SO3. In the next problem too, the same thing. It says, remember, we're trying to solve problems using those relationships I gave for sulfur trioxide in the previous relationships, because this is a good example to use. It says the number of moles of sulfur trioxide molecules in 45 grams. Again, look at what is given. We want to go from grams of sulfur trioxide, that is basically 2. We're going from grams to what? Moles of SO3. Again, we need a relationship between them. Of course, 1 mole of sulfur trioxide, this is the conversion, weighs this mass. This is the same that was used in the previous problem. The difference is that last time we looked for the mole, now we're looking for what? The mass. It says how many? The number of moles of this. Remember, the preceding problem we looked for the mass. This one we're looking for the mole. So this one we look for the mass. Here we're looking for the mole. So we start again. We have 45 grams, 45.0 grams of SO3. And then we want to convert that to what? To moles of SO3. What do we do? Of course, grams is going to go back down so that we can easily cancel that. And our mole is going to come on top. 1 mole of SO3. And then we're going to do this. Grams of SO3 and grams of SO3 cancels. And if you punch this in your calculator, you're going to be getting 0.562 mole of SO3. You go to the next one. It says the number of SO3 molecules in 121 grams of sulfur trioxide. We're still continuing with that series of problems. We want to convert the number of sulfur trioxide molecules in 121 grams. So what are we doing here? We want to convert from grams of SO3 to molecules of SO3. That's what we're looking for. That's the problem we're solving here. So again, what's the relationship? Remember, the relationship we have here is that a mole of this guy, which weighs 80.06 grams of SO3, contains how many molecules? It contains 6.022 times 10 to the power of 23 molecules of SO3. So what does that mean? We now solve the problem immediately. So we start. We have 121.53 grams of SO3 straight to 80.06 grams of SO3 will be down so that we can cancel it easily. We can cancel now. It doesn't matter. We cancel it now to tell us that we are on the right track. And then you're going to put this on top. 6.022 times 10 to the 23 molecules of SO3. And when you punch this well into your calculator, what do we get? You're going to get, the answer you get will be 9.14 times 10 to the 23 molecules of SO3. Now the next problem, it says the mass in gram of SO. Oh, this is, remember this, please. This is make this correction. This is SO3 molecules. This is SO3 molecules. We're not talking about SO2 molecules here. Please make the correction. I'm very sorry for making that mistake. It says the mass in grams. Now, so now, basic thing we are doing here is that we want to convert from molecules. Rather, we have to include this one. So we're converting from molecules of SO3 to grams of SO3. Again, we're going to use the same relationship like we used last time. We know that 6.022 times 10 to the power of 23 molecules of SO3 contains 80.06 grams of SO3. Just to let you know, this was the same relationship we used before. The difference is that the last time We solved for the molecules. Now we're solving for the mass. Again, we start from what we were given. We were given this one, 7.25 times 10 to the 21 molecules of SO3. That's where we start from. And again, you can draw your line. And then we want our molecules to be down. So I'm going to put the molecules here, 6.022 times 10 to the 23 molecules of SO3. And then on top of here, you're going to put 80.06 grams of SO3. Now, again, I'm going to cancel molecules of SO3, cancels molecules of SO3, and my answer will remain in grams. And this is going to give me 0.964 grams of SO3. That is our answer at this point. So now let's talk a little bit about formula, mass, and unit. You see, we're going to be doing in chapter 4, rather, we're going to be talking about nomenclature of and the main difference between ionic and covalent compound. But it's important here we understand this, is that for ionic compounds are compounds that contain, for ionic compounds that contain, must contain a metal plus a non-metal. That's what we call an ionic compound. Now, ionic compounds are usually non-molecular compounds. So instead of saying molecular mass, we use the word formula mass to describe their so-called molecular mass if they were covalent or molecular compound. And then we now say the number of particles they contain. Since they don't contain molecules, what they contain is just formula units. We refer them as formula unit as their number of particles. So a good example here is that it says calculate the number of formula units present in 11.6 grams of sodium chloride. The first thing I need to do is to calculate the molar mass of sodium chloride. And molar mass of sodium chloride will be sodium weighs 22.99 plus chlorine weighs 35.45. If you add both of those together, it's going to give you 58.44 grams per mole. Now, what is the formula unit now? What's the relationship? Remember, we said formula unit is a specified entity. What it simply means is that a mole of sodium chloride will contain this particular mass, 4 grams of sodium chloride. And this will be equal to, of course, again, 6.022 times 10 to the 23 formula units. So if this was a molecular compound, I would just say molecules. But because it has a metal as part of the compound, I'm going to use the word formula unit. That is how it comes in. So now, since we're looking, it says calculate the number of formula units. So since we're looking at between mass and formula unit, we're going to use these two units, and let's do it immediately. That's going to give us, you start with what you are given, 11.6 grams of sodium chloride. If you multiply it by, again, we are using these two. Since you're looking for the formula unit, you're going to put this on top, 6.022 times 10 raised to the power 23 Fu divided by the molar mass, 58.44. This is my 8. I'm going to make it beautiful a little bit. I don't like it. So it's going to be 58.44 grams of sodium chloride. Now we cancel. I'm going to use a different color. This cancels this. And whatever we have will be in formula unit. And that's going to give you 1.20 if you punch it very well in your calculator times 10 to the power 23 formula unit of sodium chloride, and that is going to be our answer. So again, remember once again, I told you it can be the Avogadro's number cannot be the mole, it cannot be the mass, but it can be any other specified entity. If you look at this problem now, it says how many hydrogen ions are present in 8.75 grams of sulfuric acid. That's what we know. So the first, since we're talking about the mass here, and we're talking about the number of hydrogen ions. Now this is a polar acid. Most of them ionize to release hydrogen ions. But how many hydrogen ions do we have here? We have 2 hydrogen ions there. So, but first, let's calculate the molar. Let's calculate the what? The molar mass of this guy. Hydrogen weighs 1.01 and 2 atoms there. Plus sulfur weighs 32.06. It has only 1 atom. Plus oxygen weighs 16. I have what? How many atoms? 4. If you add everything together, it's going to give you 98.08 gram per mole. So what it simply means, if you look at this combo, what it simply means is that this molecule contains 2 moles of hydrogen ion. So what that simply means is that 2 moles of hydrogen ion. Of course, a mole of hydrogen ion will weigh 1 Avogadro's constant, 1 Avogadro's number. So if it is 2 moles, we weigh 2 times 6.022 times 10 raised to power 23 hydrogen ions. That is what we're going to have in it. Now remember, we're looking for how many hydrogen ions present in this particular mass, 8.75 grams of this. Now, and of course, what it means in this formula, what it means is that 2 moles of hydrogen will be equivalent to 1 mole of this, and the mass of 1 mole of sulfuric acid is this. So we just say this will be equal to 98.08 grams of H2SO4, which happen to be the mole of this, its mole. If we don't need the mole, that's what we're not bringing in the mole, because we know this is also equivalent to 1 mole of H2SO4. So there, what are we using? The 2 things we're looking for, we don't need the moles here too. We're looking for ions of hydrogen. Let me use a different color. We want to convert from what? Grams of this guy to ions of hydrogen. So we're using this conversion factor. So it makes sense, because our grams, we cancel with the grams, and we're going to be left with this. And then if we solve this problem, so what do we get? Let's move. It's going to be 18.75 grams of H2SO4 will multiply. This will multiply, of course, because we want to cancel grams of H2SO4. This is going to be under. So this is 98.08 grams of H2SO4. Let's just cancel first to make it easier. Grams of H2O4 goes away with grams of H2O4. And then we now have our 2 times 6. 2 times 6.022 times 10 to the power of 23 hydrogen ions. And when you punch this in your calculator, what do you get? You get 2.30. Let me make that too beautiful. So you're going to get 2.30 times 10 to the 23 hydrogen ions are contained in this particular mass of sulfuric acid. Now, always pause the video, try solving these problems yourself, come back and check for comprehension. It pays to always practice on how to do these problems. Like I said, I always put a lot of problems, and the reason why I do that is for us to just practice. It says calculate the number of moles of potassium ions, K plus, in 6.90 grams of this. So again, we want to convert from grams of potassium sulfate to moles of potassium ion. We'll try to write out. The first thing you need to do, since grams is involved, of this guy, we want to calculate the molar mass. Again, if you calculate the molar mass, that will give you 2 atoms of potassium, one weighs this. So if you multiply by 2 plus sulfur weighs 32.06 plus there are 4 hydrogen atoms there. And if you add everything together, you're going to have 174.26 grams of K2SO4. Now, that is it. Then the next thing, what is the next thing we do? We now find the relationship. Now, if you look at this, there are 2 moles of potassium ion inside 1 mole of this gas. So we comfortably write the relationship that there are 2 moles of K plus in 1 mole of this guy. Of course, although we don't need the mole, but let's just start from there. 1 mole of K2SO4. But we know that 1 mole of K2SO4 weighs this mass, so it's going to be equal to 174.26 grams. That's too close. 26 grams of K2SO4. Now, we don't need this one. The basic 2 units we need is these guys. So that's what we want. That's what we need. If we now solve the problem, what it means, starting from what you were given, you were given 6.90 grams of K2SO4. Again, since we are using these 2, we want to remove the mass. So we're going to put the mass down. So this is going to be 174.26 grams of K2SO4. Again, I want to cancel before I move on. Grams of this, cancel grams of this. That shows you that you're correct. And then you're going to put 2 moles of potassium ion. And when you multiply your numbers, if you multiply across and then divide, you're going to be getting 0.0792 moles of potassium ion. And this is what you get. So the next thing we're going to, so at this point, we've come to an end of our various problems in the mole concept and mole conversions. We're going to have to be doing more problems on the worksheets. And again, you can always feel free to pause the video, watch this, solve the problems, and come back to them. It looks like a long video. Always take a breather along the line and always come back to watch the video and then understand and practice for better comprehension. The next thing we'll be talking about is what we call the mass percent. Mass percent simply means the way we calculate the percentages of each element in a particular compound. Remember, 1 mole of a particular compound will weigh the molar mass or the formula mass of that compound. So if we get the mass of that particular element, like we have here, and divide it by the molar mass of that compound and multiply by 100, we're going to get the mass of that particular element. So the best way to put this is to take some examples here. Again, I'm coming back to my favorite guy, SO3 minus. It says, what is the mass percent of sulfur and oxygen in SO3? Again, I know I calculated this earlier. I'm going to calculate it again because we're going to be needing the individual mass. If you look at this compound, what it means is that sulfur weighs 32.06 grams. That's what sulfur weighs. Plus oxygen weighs, there are 3 oxygens here. Rather, so the 3 oxygens is going to be weighing, it's going to be 3 times 16.00. Now, of course, if we add both of these things together, it's going to give us 80.06 like we did earlier. What this simply means, remember, this is sulfur, this is oxygen. Here, if you multiply oxygen, oxygen is going to give you 48.00 grams. Of course, sulfur here of oxygen. For sulfur, what do we have? Let me clean that and then bring it down. So what I'm going to still have will be 32.06 grams of sulfur. Now, if I'm going to calculate the first one, let me try to calculate them in P. So if I want to calculate percentage of sulfur, what it simply means is that the mass of sulfur I have here is 32.06. If I divide it by the molar mass, which is 80.06, this is gram, it's going to cancel out times what? 100 over 1. If you multiply this well, you're going to get 40.04% of sulfur. On the other hand, if you do this one, it's going to be oxygen, percentage of oxygen. Okay, let me try to make a short thought. Percentage of oxygen will be 48.00 grams divided by 80.06 grams times 100. Again, grams, we cancel grams. I didn't even cancel my grams here. And if you multiply this is going to give you 59.0, no, that's going to give you 59.96% of oxygen. So this is how we do mass percent. Mass percent is just a simple way of calculating the percentage of elements. So another problem here, it says calculate the percentage by mass of oxygen in this guy. Now what are we going to do? Again, we're going to calculate the molar mass of this. In calculating the molar mass of this, remember, calcium has 3 atoms. So this is 3 times, it weighs 40.08. This is only calcium plus how many phosphorus here? Look at this bracket. There's 1 atom inside. Because of these two, it will multiply that 1 subscript here. So we're gonna have 2 atoms of phosphorus. And 1 atom weighs 30.97 plus, again, look at this one. This oxygen here has 4 atoms inside. The parenthesis, of course, this 2 is going to multiply this, and it's going to be 8 atoms of oxygen. Now, we're not interested in any other one. The only thing we're asked to calculate here is oxygen. So if I'm going to calculate them individually. So if you multiply this will give you 120.24 grams of this guy. This will give you plus 61.94 grams of this guy. And then this will give you plus 128 grams. Okay, I want to maintain the number of digits I have there. So this is going to give me 128.00 grams of oxygen. And if you add everything together, the total mass is going to be 310.18 grams. And then we're looking for only percentage of oxygen. Oxygen there will be, oxygen that we have there weighs a total of what? 128 grams. So this will be 128 grams of oxygen divided by the total molecular mass, 310.18 grams. We're going to multiply this by 100, and that is going to give you 41.3% of oxygen is contained in calcium phosphate. The next problem. Now, the next problem is an interesting word problem. That's exactly what this. I usually like this kind of problem. It says ammonia and ammonium nitrate are commonly used agricultural fertilizers in agric industry. It says which of these two contains the higher mass of percentage of nitrogen? Quantitatively justify and explain. Quantitatively means solve the math. That is the logic I need. So first, I'm going to calculate the molar mass of this guy. The molar mass of nitrogen weighs 14.01 plus how many hydrogen do you have there? 1.01, and this is going to be 17.04 grams per mole of 1 mole of this. And I go to ammonium nitrate. In ammonium nitrate again, if you look at this, I have 2 nitrogen here, 2 nitrogen atoms. So it's going to be 2 atoms of nitrogen. Each nitrogen weighs 14.01 plus, what else do I have there? Hydrogen. There are 4 atoms of hydrogen, 1.01. And then there is 3 atoms of oxygen. And if you add everything together, this is actually going to give you 80.06 grams. 80.06 grams. That's what we're going to be getting at this point. Grams in 1 mole of this guy. Now, if you add this together, now, if you multiply 2 times this is going to give us, there is a total of 28.02 grams of ammonia in this, of nitrogen in ammonium nitrate. So now let's calculate the first one. Let me just try to make a percentage of nitrogen in ammonia will be, I have only 14.01 grams of it there. You can put just grams there, it doesn't matter. So this would divide 17.04 times 100. This will give us 82.2%. Now, what about the second one? Let's see. In B part, we're going to calculate percentage of nitrogen in ammonium nitrate. And that will be, again, here it has, the mass is 28.02, put your grams, divided by, the mass is 80.06, 80.06 grams. If you times it by 100, and that's going to give you what? It's going to give you 35% of nitrogen. Now, you see, ordinarily, if you did not solve this problem, you can make a very, erroneous assumption that since this one contains 28 grams of nitrogen by mass, that it actually has more percentage of oxygen. But that is not. Percentage of nitrogen, no, that is not. And the reason why that is because the mass of this guy is 80.06 and the mass of this guy is 17.06. So when you divide a number by a bigger denominator, it tends to make it very much more smaller. So that is why you see that in both of these two guys, ammonia actually contains a higher percentage of nitrogen of 82.2%. And that eventually is our last problem. And we've come to an end of this lecture. Thank you once again for listening. Once again, remember that if you have any problems in any of these problems, you can always see me during my office hours, or anytime you bump into my office, talk to me. I told you I have an open office hours. And if you also have the time, you can always go to tutoring center or seek other helps for better understanding or clarification if need be. Once again, thank you for listening, and do have a wonderful